Computer-aided engineering and engineering informatics, technologies, algorithms, programming, and engineering applications. A comprehensive exploration in computer-aided engineering, CAE, or engineering informatics is a broad domain encompassing the use of computer software to aid in engineering analysis tasks. These tasks include finite element analysis, FEA, computational fluid dynamics, CFD, multibody dynamics, MBD, and optimization. CAE tools are integral in the engineering product development lifecycle, supporting design validation, simulation, and decision-making processes. With the advent of powerful computational resources and advanced numerical methods, CAE has evolved into a cornerstone technology in modern engineering disciplines including automotive, aerospace, civil, mechanical, and biomedical engineering. Historical evolution of CAE. The origins of CAE trace back to the mid-20th century, with the development of the finite element method, FEM, in the 1950s and 1960s. Initially employed for structural analysis in aerospace applications, FEM's computational advantages led to its integration into commercial software packages by the 1970s. Concurrently, advances in computational fluid dynamics, CFD, enabled the simulation of fluid flow and heat transfer phenomena. The 1980s and 1990s witnessed the proliferation of CAE tools as hardware became more affordable and software more user-friendly, culminating in integrated CAE suites that enabled multi-physics simulations by the early 2000s. Core disciplines of CAE: finite element analysis, FEA. FEA subdivides complex geometries into smaller, manageable elements, solving governing equations at discrete nodes. Applications include stress analysis, thermal analysis, vibration analysis, and fatigue prediction. Modern FEA software packages such as ANSYS, Abacus, and Nastron facilitate linear and nonlinear analyses, accommodating complex material models and boundary conditions. Computational fluid dynamics, CFD. CFD involves numerically solving the Navier-Stokes equations to analyze fluid flow, turbulence, combustion, and heat transfer. It enables the prediction of fluid behavior in domains ranging from aerospace aerodynamics to internal flows in HVAC systems. Key software tools include Fluent, OpenFOAM, and STAR CCM+, often employing turbulence models such as K-epsilon, K-omega, and large eddy simulation, LESS. Multibody dynamics, MBD. MBD examines the dynamic behavior of interconnected rigid or flexible bodies under the influence of external and internal forces. It is essential in simulating mechanical systems such as suspension mechanisms, robotic arms, and biomechanical models. Tools like MSc Atoms and SIMPAC are widely used for dynamic analysis and system optimization. Optimization and design exploration. CAE tools support design space exploration and optimization through algorithms like gradient-based methods, genetic algorithms, and surrogate modeling. These methods enable the identification of optimal configurations subject to performance, cost, and manufacturability constraints. Integration in product lifecycle. CAE is embedded within the Product Lifecycle Management (PLM) framework, facilitating virtual prototyping and reducing reliance on physical testing. Engineers can simulate multiple design iterations rapidly, accelerating development cycles and enhancing product reliability. Integration with computer-aided design (CAD) and computer-aided manufacturing CAM, ensures seamless transition from conceptual design to production. Digital twin and real-time simulation. The concept of the digital twin, a real-time digital replica of a physical asset, leverages CAE models updated with sensor data to predict performance and maintenance needs. Real-time simulation capabilities, driven by high-performance computing, HPC, and cloud-based platforms, enable engineers to perform large-scale simulations with reduced turnaround time. Challenges and limitations. Despite its advantages, CAE faces several challenges. 1. Modeling accuracy. The fidelity of simulations depends on the accuracy of input parameters, boundary conditions, and material models. Errors can propagate, leading to misleading results. 2. Computational cost. High-resolution models require significant computational resources, which may limit accessibility for small and medium enterprises, SMEs. 3. User expertise. The effective use of CAE tools requires multidisciplinary knowledge in physics, numerical methods, and software operation, posing a barrier for non-specialists. 4. Verification and validation, V&V. Ensuring that models are both mathematically correct and represent physical reality accurately remains a critical concern in safety-critical applications. Future trends. The future of CAE is poised for transformative developments driven by technological innovations. 1. Artificial intelligence, AI, and machine learning, ML. AI/ML algorithms can enhance simulation efficiency, automate meshing, detect anomalies, and develop predictive models. 2. Cloud-based CAE. Cloud computing democratizes access to high-performance simulation tools, enabling seamless collaboration and scalability. 3. Multiscale and multiphysics modeling. Advancements in modeling techniques allow for the integration of phenomena across different spatial and temporal scales, which is essential for complex systems. 4. Augmented reality, AR, and virtual reality, VR. AR/VR interfaces offer immersive visualization of simulation results, aiding in design reviews and stakeholder communication. Core computational technologies in CAE. CAE encompasses a suite of sophisticated technologies that simulate diverse physical phenomena. 1. Finite element analysis, FEA. FEA is a numerical technique for analyzing the structural, thermal, and vibrational behavior of mechanical components. It decomposes complex geometries into finite elements and applies stiffness matrices to solve problems using variational methods. Key applications include stress-strain analysis of components, thermomechanical performance under varying conditions, modal analysis and natural frequency determination. 2. Computational fluid dynamics, CFD. CFD analyses fluid flow, heat transfer, and species transport by numerically solving the Navier-Stokes equations. Common applications span aerodynamic profiling in automotive and aerospace engineering, thermal management in electronic devices, fluid mixing in chemical processes. 3. Multibody dynamics, MBD. MBD models systems with interconnected rigid or flexible bodies. It supports the kinematic and dynamic analysis of mechanisms under applied forces and constraints. Common MBD use cases include vehicle suspension design, Robotic motion planning. Machinery kinematics. 4. Electromagnetic, simulation. Simulation tools solve Maxwell's equations for evaluating electromagnetic fields in high-frequency and low-frequency regimes. Applications include antenna design and RF circuit analysis, electric motor performance, signal integrity in PCB layouts. 5. Optimization and design exploration. CAE platforms include optimization modules for automated design iteration using topology optimization, parametric studies, multi-objective optimization using evolutionary algorithms or adjoint solver algorithms and numerical method. The effectiveness of CAE is grounded in advanced numerical algorithms that discretize, solve, and refine physical models. 1. Discretization method. To transform partial differential equations, PDEs, into algebraic systems, various discretization techniques are employed. Finite element method, FEM, suitable for solid mechanics and thermal problems. Finite volume method, FVM, dominant in CFD applications for mass and energy conservation. Boundary element method, BEM, effective in acoustics and electromagnetic scattering problems. 2. Solvers and linear algebra. CAE solvers use various mathematical techniques to handle linear and nonlinear problems. Direct solvers, Gauss elimination, Liu decomposition. Iterative solvers, BICGSTAB, conjugate gradient, GMRES. Nonlinear solvers, Newton-Raphson, Broyden's method. Time integration, Runge-Kutta, Crank-Nicolson for dynamic systems. 3. Adaptive meshing and refinement. Adaptive mesh refinement, AMR, algorithms dynamically improve solution accuracy by concentrating computational effort on regions with high gradients or discontinuities. 4. High-performance computing, HPC. Large-scale CAE simulations are accelerated using parallel computing paradigms. MPI-based domain decomposition. OpenMP for shared memory parallelism. GPU acceleration for dense matrix computations and iterative solver programming in CAE. Programming plays a pivotal role in the development, customization, and automation of CAE workflows. 1. Core programming languages. Low-level programming languages such as Fortran, C, and C++ are widely used to build CAE solvers due to their computational efficiency and memory control. 2. Scripting and integration. Scripting languages like Python and MATLAB are employed for preprocessing, geometry generation, meshing, post-processing, data analysis, visualization, and automation. Python. API integration with tools like OpenFOAM, Abacus, and COMSOL. MATLAB. Common in control system simulations and signal processing. 3. Plugin and UDF development. Users often develop custom features using user-defined functions, UDFs, in Fluent, user subroutines, UMOT, VUMIT, in Abacus, solver customization in OpenFOAM C++ framework. 4. Data analytics and visualization. libraries such as NumPy, SciPy, Pandas, Matplotlib, and VTK are critical for statistical analysis, result interpretation, and graphical representation. Engineering applications of CAE technologies are extensively adopted in various engineering domains for product innovation and validation. Automotive industry. Crash simulation, high-speed impact analysis with PHI. Engine design, CFD modeling of combustion and thermal loads. NVH analysis, sound and vibration characterization of vehicle cabins. Aerospace engineering. Aerodynamics, CFD-based lift, drag, and flow separation studies. Structural analysis, fatigue life prediction and composite material testing. Thermal control, heat dissipation in avionics systems. Civil engineering. Structural mechanics, earthquake resistance and load path analysis. Fluid dynamics, urban airflow and pollutant dispersion. Geotechnical analysis, soil structure interaction under dynamic loads. Biomedical engineering. Biomechanics, joint stress distribution and prosthetic design. Biofluids, blood flow modeling in cardiovascular systems. Medical device simulation, thermal ablation and drug delivery efficacy. Energy systems. Wind turbine simulation, blade aerodynamics and structural fatigue. Heat exchanger design, CFD modeling of flow patterns and temperature gradients. Combustion modeling, simulation of turbulent combustion in engines and gas turbines. AI and quantum technologies in CAE. The integration of artificial intelligence, AI, and quantum computing marks the next frontier in CAE advancement. Artificial intelligence in CAE. AI enhances CAE capabilities by enabling surrogate modeling. Machine learning models approximate complex simulations for faster evaluations. Automated mesh generation. Deep learning identifies optimal mesh densities and refinement zones. Predictive maintenance. Trained models forecast component failure from CAE-derived stress, strain histories. Design optimization. Reinforcement learning and genetic algorithms explore vast design spaces. Quantum computing in CAE. Quantum computing holds transformative potential for CAE through its ability to solve high-dimensional problems exponentially faster. Quantum annealing. Applied in topology optimization and complex constraint satisfaction problems. Quantum algorithms. For solving sparse linear systems, which underpin many PHI and CFD problems. Hybrid quantum classical models. Combine quantum subroutines with classical solvers to reduce computation time in parameter estimation or uncertainty quantification. While still in early stages, these technologies promise to redefine the computational boundaries of engineering simulation. Challenges and future direction. CAE continues to evolve in response to the increasing computational demands, growing integration complexity, and evolving industrial expectations. Challenges. Accuracy versus cost. Trade-off between model fidelity and computational efficiency. Validation. Ensuring numerical results correlate with experimental data. Usability. Democratizing CAE for non-experts through intuitive interfaces. Emerging trends. AI integration. surrogate modeling, automated meshing, and design space exploration. Quantum CAE, leveraging qubits for solving high-dimensional models. Digital twins, real-time simulation models synchronized with operational data. Cloud-based CAE, platform as a service, PaaS, for scalable simulation resources. Multi-scale modeling, bridging nano to macro scales for holistic system behavior. Immersive visualization, VR, AR for enhanced interaction with simulation outputs. Conclusion: computer-aided engineering represents a foundational pillar of modern engineering practice, enabling simulation-driven design, validation, and optimization. By integrating physics-based modeling, advanced numerical algorithms, and software programming, CAE accelerates innovation while minimizing costs and risks. With the rise of AI and quantum computing, CAE stands on the brink of a transformative leap, unlocking simulation fidelity and speed beyond classical constraints. The convergence of these technologies will further embed CAE as a core enabler of sustainable, intelligent, and high-performance engineering systems.